Yes, the intricacies of physics. I just got a question that is the sort of thing that I would normally address in class and clarify, and obviously this year things are a bit different. But I think I'd like to take an opportunity to clarify an issue and address the question that I got, and then just kind of address it to everybody. So the scenario is going to be with an object hanging from a string. So let's just say I have a ball and a string. No, it's not a ball, it's like a mouse receiver. This thing is probably as old as most of you guys, but here it is hanging from a string. So let's just assume the string is massless and we have this object hanging from a string. So we have this situation that we're looking at in two different ways. So in the video that I had posted where Diana, the physics girl, has a cow on a string, and she is talking, about this toy little cow and the forces acting on that cow, and she draws a free body diagram for it. But that seems contradictory to what I've said before about action-reaction pairs. So let me see if I can kind of clarify that a little bit. So let's see if I can kind of minimize me a little bit. Oh, too small, too small. Sorry, I don't know why that's funny to me. So I have two different scenarios, and to really explain that this truly is two different scenarios happening here, let me express that by just saying, hey, look, this is truly, I'm going to split this screen right down the middle. This is truly two different scenarios, or at least it's the same scenario, but I'm looking at two different, completely different aspects of it. So in terms of Newton's third law with action-reaction pairs, for every action force is equal and opposite reaction force. So acting on this object, let's just call it a ball or a cow, whatever it is, it's a pig. It's a pig with wings. It's a flying pig. It's when pigs fly. Okay, so here we have this thing on a string, and it has a force acting on it. That force acting from the center of mass, I'm going to call that mg. And so that force acting on it is being acted on from Earth. So we have, the big giant Earth acting on this little tiny ball on a string. So there is the ball, and here is the big Earth. That is the ugliest looking letter E I've ever made. So this is the Earth, and that's that little tiny thing. So the Earth acts on this little pig thing, and the pig thing then in turn acts on the Earth, right? Action-reaction forces, the two are acting on each other. So there is a force acting on the pig, and then, let's just say that this was the Earth down here in this perspective. Let me go ahead and get rid of this guy, because this is just my little sort of like third-person perspective that I was drawing. And so, there's a force of the pig acting on the Earth up in that direction. So that's my action-reaction pair. So if I were to make the pig suddenly disappear, this force would go away, and this force also would go away. So the thing about action-reaction pairs is that this force, this object acts on this object here, and then this one acts on the other. So object 2 acts on object 1, object 1 acts on object 2. And the forces are on two different objects. Let's look at a free body diagram though. So in this case, I'm looking at a free body diagram where I'm trying to draw the forces that are acting solely on this object. So let me off to the side draw a dot that simply represents this object still being my pig. I'm going to draw my pig again. Sorry, I can't help it. There's a reason why physics likes pigs. I just don't know that reason. So I'm going to have a force of mg acting down, right? This is my free body diagram. And then of course there's also the force of tension acting up. So I'm going to draw that as well. And assuming that the pig is not accelerating in any direction, these two forces should be equal and opposite. So in the case of the free body diagram, I'm trying to show the forces that are acting on the pig. I'm showing just the forces that are acting on this object in order to use Newton's second law. So basically, action-reaction pairs refer to Newton's third law, to where free body diagrams are more trying to utilize Newton's second law, right? In this case, I'm going to say, okay, the sum of all forces acting on the pig in the y direction is equal to the force of tension minus mg, because that's acting in a downwards direction, and the whole thing is equal to the ma of the pig, right? That's the mass of the pig times the acceleration of the pig. And if he's not accelerating, I can then say it's 0. Sure, why not? Which then in turn means that the force of tension must be equal to the mg. So this is just looking at the forces actually acting on this one singular object, and it ignores all other objects in the universe. Versus an action-reaction pair, you are forced to look at the two objects interacting with each other. How just it allows you to say that one force acting on one, the force of one object acting on two is the same as the second force acting on the first. Hope I said that right. Let me elaborate one more thing as to why it's important for us to make this distinction with action-reaction pairs. Let me, as I try and put my tablet away, let me also kind of express it this way. What if I instead, make myself big again, what if instead I said something like, take this piece of paper, take my Spectrum bill, which I've been working on for 2 weeks. Not my favorite company in the world to deal with. So, I want to apply, I'm the strongest man ever on the earth. I want to apply just a massively large force onto this piece of paper. So how do I do that? Oh, okay, so I could maybe put the piece of paper between my two hands and press on it. But what if I'm not allowed to do that? What if I'm only allowed to use one hand? Then how can I apply a massively large force onto it? Okay, I could try and press it down into, onto the wall or onto my table. But again, I can make the rule that I'm not allowed to use any other objects other than my one hand. That's it. It's my only object. How can I apply a large force to this object? And the answer to that is to get it to accelerate. I can only apply a large enough force onto this piece of paper as the paper can apply onto me. Newton's third law. And so my best chance at being able to apply a large force onto it is to maybe, it's such a point, I'm just getting it to accelerate at such a high rate that it will then in turn be able to apply a large force onto my hand, and then my hand can then apply a large force onto the paper. So Newton's third law and Newton's second law can go hand in hand, but I just wanted to try and go over some of the differences between the two, especially from a conceptual standpoint, so we can think of the two kind of separately, and hopefully that clarifies things at least a little. There can be some confusion there, totally understood. So action-reaction pairs are on two different objects, and so the only time in which you'll have action-reaction pairs coming up in free body diagrams would be, let's say for example, if I had the ceiling, or better yet, I'm trying to use my mouse at the moment. This is my hand. Oh my God, is that a bad hand? But what if I want to know about the forces acting on my hand? So then I could separately have a free body diagram. So I have this, this is my free body diagram for the pig thing, the flying pig, but I also have another free body diagram for my hand, right? So this, I'm going to label this as a P for pig, so I'm using my mouse right now. And then I'm going to also have a separate free body diagram for my hand, so I'm just going to put an H for a hand. And so in that case, I have the force of tension acting down, right? Because the string is pulling down on my hand. And then I have the force of like my finger pulling up on the string. So I'm just like isolating a specific spot, maybe on my hand, or a spot at the top of the string. And so my hand is pulling up on the string. And so that, I'm just going to say the force of the hand. So that's going to be my F sub H. And then this one is the force of tension, okay? So the case in which the action-reaction pairs comes into play with free body diagrams would be where this force and this force are the same force, okay? but they're acting on separate objects. So the only case in which action-reaction pairs actually come up within the same problem will be as if you have an action-reaction pair, but the action-reaction pair is going to be drawn on two different free body diagrams. This is one free body diagram. This is a separate free body diagram. Okay? So if I were to cut the string, I'm going to get rid of this force, that goes away, and I also get rid of that force on these two separate objects. Gosh, I hope that clarifies things. So let me know if it doesn't, and I'll see you next time.